I want you to picture something for a second. Just imagine the sheer overwhelming volume of text that gets generated every single day.
Oh, it's staggering.
And I'm not even talking about, your group chats or what you texted your mom this morning.
Which is still a lot of text, to be fair.
It is, but I mean the heavy hitters.
Yeah.
The serious stuff. We're talking millions of news articles every 24 hours, mountains of medical records, scientific papers.
Legal contracts, patents.
Mm-hmm.
It's an absolute ocean of words.
Exactly. And for a human being, it's physically impossible to keep up. You could read for 1,000 lifetimes and not even put a dent in what's published in a year.
It's the definition of information overload.
Right. But here's the kicker. We just assume computers can handle it. We think, just feed it to the AI.
Yeah.
But for a standard computer program, all of that valuable knowledge, it's just noise.
It's unstructured chaos.
Yeah.
And that's the fundamental disconnect, right? To a computer, a brilliant medical diagnosis isn't information. It's just a string of bytes.
Yeah.
It doesn't inherently know that aspirin is a drug or that London is a place.
It's just characters on a screen.
Exactly.
And that is the problem we are tackling today. We're doing a deep dive into information extraction, or IE. We're basing this on a really comprehensive text by Ralph Grishman, looking at how we take that whole mess of free text and turn it into an actual usable meaning.
And the mission here is really specific. It's not just reading in the way you or I would read a novel. It's about transforming that messy free text into structured data. It's the difference between a computer just displaying a document and a computer actually understanding that Captain Ahab is a person.
And that he has a very specific and slightly obsessive job.
A very obsessive job, yes.
I love that example from the source material. It uses this sentence. Captain Andrew Ahab was appointed vice president of the Great White Whale Company of Salem, Massachusetts. Now, I read that and I see a whole story. But what does the machine see?
Well, without information extraction, it sees nothing, a sequence of letters. But the goal of IE is to automatically identify the entities.
The people, the places.
The people, the organizations, the locations, and the relationships between them. So the output isn't text anymore. It becomes structured tags.
Like a database entry.
Exactly. It wraps Andrew Ahab in a person tag. It wraps Great White Whale Company in an organization tag.
So it's literally converting literature into data points.
Precisely. Turning narrative into a database you can actually search and analyze.
Which sounds simple in theory. You just tell the computer, go find the names. But the source makes a really great point about why you can't just use a dictionary for this. I mean, why not just load up a dictionary and say, check against this?
That's how, older computer analysis used to work. You'd look up a word. Is it a noun? A verb brought? But the problem with the real world is that most texts are packed with proper names that just aren't in the dictionary.
Like startup names or some weird band names.
Exactly. Or Fugu Motors.
Fugu Motors. That's the example from the text.
Right. So you have a sentence about Fugu Motors, and if your system doesn't know that's a single unit, a company name, the whole analysis just falls apart.
The dictionary would just tell you Fugu is a poisonous fish.
And Motors is a plural noun. It won't tell you it's a corporate entity, which, now that you mention it...
Fugu Motors sounds like a terrifying car company. I would not drive one.
Me neither.
But this brings up the issue of context, or what the source calls domain specificity. You can't really build one universal rater for everything, can you?
Not easily, no. What counts as an entity actually changes depending on what you're reading. If you're mining chemistry articles, your entities are chemicals, compounds.
But for biology, it's...
species, proteins, genes.
And if I'm reading, say, the Wall Street Journal?
Then you're hunting for the big three. People, organizations, and locations. That's pretty much the standard for general news.
So let's get into the mechanics. How does the machine actually do it? If we want to find Fugu Motors in a stack of newspapers, we obviously can't have a list of every person on Earth.
No, that's impossible. New people are being named every day. So you build what's called a tagger. And at its most basic level, this starts with pattern recognition. You use what are called regular expressions.
Which are basically just strict rules for text patterns.
Precisely. So think about how you'd recognize a company name in English. You might look for a capitalized word followed by...
Or SORP, or ink.
Right. So the formula is capitalized word plus corp equals organization.
Simple enough.
And for people, a strong signal is Mr. plus capitalized word. That's a classic. But the source mentions something really clever here. We can call it the Fred Smith rule.
I marked that one down. It's surprisingly simple, but so effective.
It is. Imagine you see Fred Smith, 42 was appointed,
Yeah.
whatever. The machine doesn't know who Fred Smith is,
Right.
but it sees the pattern. Capitalized word plus comma plus a number below 100.
And that structure almost always means a person and their age.
Almost always. It uses the context, the comma, and the number to define the word that came before it.
That's really smart. But there's a catch, because writers are lazy. They'll call him Fred Smith in the first paragraph, but then just Mr. Smith, or even just Smith, later on.
That is the alias problem, and it is a huge headache for these systems. A good system needs to know that Fred Smith and Mr. Smith in the same document refer to the same entity.
And it helps with ambiguity, too. The text gave the example of Robert Smith Park.
Oh, that's a classic. Is Robert Smith Park a person?
Or is it a park named after Robert Smith?
Exactly. And the computer has no idea. But if the alias system sees Mr. Park later in the text, it can look back and say, aha, Robert Smith Park was a person.
So it's constantly looking backward and forward to figure things out. But this brings me back to the effort involved. Writing all these little rules by hand. If capital letter plus comma, that sounds exhausting. And brittle.
It is incredibly laborious. And you'll never catch every exception. That's why the field moved away from hand-coded rules toward what we call supervised training.
Okay, this is where we stop programming the rules and start teaching the machine.
We let it teach itself, essentially. You take a massive stack of documents, a corpus, and you annotate them by hand. You sit people down and have them highlight every name, every location, every organization.
That sounds expensive and really boring.
It is very expensive and very boring. But once you have that labeled data, you can train a probabilistic model on it. The source highlights the hidden Markov model, or HMM.
Okay, let's pause on that, because hidden Markov model is one of those terms that sounds like, Star Trek technobabble.
It does.
So what's it actually doing, in plain English?
Think of it like a guessing game based on sequences. The model isn't just looking at the word Smith in isolation. It's looking at the invisible state or tag behind the word. And it learns that the probability of a tag depends heavily on the previous tag.
So context is king again.
Always. If the machine sees the word Mr., it learns from that training data that there's a huge probability, like 99%, that the next word has the person tag.
I just saw Mr., so I'm going all in that the next word is a name.
That's exactly it. It's not guessing based on Smith itself. It's guessing based on the likelihood of the sequence. But again, that takes thousands of hand-labeled documents. What if you don't have the time or money?
Then you try the lazy way.
We prefer to call it semi-supervised or bootstrapping.
Bootstrapping. I thought this was one of the coolest concepts in the whole text. How does it work?
So this is for when you only have a few known names to start with. We call them seeds.
Yeah.
Let's say you have a list of just 10 car companies.
Okay.
You feed those 10 names to the machine and tell it to find them in a massive pile of text.
So it finds Ford, Toyota, and our friend Fuga Motors. Then what?
It looks at the context around them. It might notice that every time one of those companies appears, it's followed by the phrase, announced a recall.
A common occurrence, sadly.
Right. But now, the machine treats announced a recall as a clue, a pattern. It goes back through all the text, finds other words that are followed by announced a recall, say General Motors, and it assumes.
Hey, if it announced a recall, it must be a car company, too.
You got it. It learns to spot the entity by the company it keeps.
And then it adds General Motors to its list of seeds, and the cycle just repeats. It literally pulls itself up by its bootstraps.
Precisely. It expands its own dictionary at a self-feeding loop.
So we've got names. We can find Fred Smith, but the source material points out that identity is more than just a name. It brings up this concept of entity extraction.
This is a really critical distinction. A text rarely uses the full name every single time. Writers use pronouns he, she, it.
Or descriptions like the investment house instead of Lehman Bros.
Exactly. And if you have a sentence like, Lehman Bros collapsed because it took too many risks, the computer has to know that it refers back to Lehman Bros.
Otherwise, you just have a sentence about a floating it taking risks.
Which is meaningless. That process is called coreference resolution. You're linking all those mentions to the same entity ID. And if you think pronouns are hard, wait until you get to spelling.
Oh, I can only imagine. The source mentions the Bill Clinton problem.
Right. William Jefferson Clinton versus Bill Clinton. A human knows that's the same person instantly. A computer has to be taught that Bill is a standard nickname for William.
But it gets way harder.
It gets way harder with transliteration. The text uses the example of the former Libyan leader Muammar al-Gaddafi.
Oh, right. I remember seeing his name spelled a dozen different ways. Gaddafi with a Q, Gaddafi with a G.
Sometimes with a K. Because it's being translated from a non-Roman alphabet, Arabic in this case, there isn't always one standard English spelling.
Yeah.
The system has to figure out that all these variations are the same person,
Because if it doesn't, you end up with 3 different files for the same guy.
which defeats the whole purpose. You want one profile, not 3.
Okay, so we've identified the players. We know who Fred is. We know who Gaddafi is. But a list of names isn't a story. We need the connections. This brings us to relation extraction.
This is moving from the who to the what's the connection. Things like family, employment, citizenship. We're looking for what we call binary predicates. Person X works for organization Y.
But just like with names, people say things in all sorts of weird ways. The text compares Fred lives in Zermatt with Zermatt resident Fred.
Or Fred resides in Zermatt. The phrasing changes, but the relation, the located in relation, is exactly the same.
So the machine has to do some real syntactic analysis.
It does. It can't just look at word order. It has to look at the sentence structure. It often breaks the sentence down into a dependency tree. It traces a path from Fred to Zermatt, and even if the words are rearranged, that path often goes through the same core verb, like live or reside.
It's seeing the skeleton of the relationship.
It is. But this is where it gets really interesting and honestly a little risky. The source talks about the danger of the machine learning the wrong thing. They call it semantic drift.
Yes, this is a fascinating pitfall of that bootstrapping method.
Remember the glimbots eating lettuce?
Right, finding patterns from seeds.
So let's say you want to find the relation located in. You give the machine a few seeds. But who appears in the news most often with locations?
Politicians. The governor of Texas, the senator from New York.
Exactly. They're always tied to their geography. So the machine starts seeing patterns. It sees phrases like is governor of or represents, and it thinks.
Ah, these must also mean located in.
And suddenly the definition drifts. The machine starts thinking that born in, represents, and is governor of all mean the exact same thing as located in. It loses all the nuance.
It's categorizing a politician representing a state as just being located there.
Right. The semantic meaning has drifted away from your original goal because the correlation was just too strong.
That's wild. It's like the computer is getting confused by correlation versus causation.
Precisely. And it's really hard to untangle once the machine learns it. To scale up without this drift, researchers sometimes use something called distant supervision, which is basically cheating.
Cheating. Okay, I'm listening.
Well, instead of relying only on the text, you use an existing database. Let's say you have a database that already knows Fred works at Fugu Motors.
Right.
You tell the machine, go find every single sentence in this million-document pile that mentions both Fred and Fugu Motors.
Okay.
And then here's the cheat. The machine just assumes that every single one of those sentences is expressing the works at relationship.
But that seems incredibly noisy. What if the sentence is, Fred, who used to work at Fugu Motors, now hates them?
That is the risk. It's
Yeah.
noisy. But the theory is that if you have enough data, the correct pattern like employed by will appear so much more often that the signal drowns out the noise.
It's a numbers game. Trading precision for massive volume. Okay, so we have names, we have relations, but life isn't static. Things happen. This brings us to event extraction.
And this is the highest level of complexity. Relations are usually between two things. Events can have multiple arguments.
The example they give is, Mary sold the phonograph to Joan for $10.
Right. Think about all the moving parts there. You have a buyer, Joan, a seller, Mary, an item, the phonograph, and a price, $10. If the computer misses just one of those.
Understanding is incomplete. You lose the price, you don't know the value.
Exactly. And you have to decide what even counts as an event. They talk about scenarios. This is about scope. For a terrorist attack, do we track the explosion and the injuries as two separate events?
That seems messy. You'd want to know they're related.
Right, so you combine them into one big attack scenario. It helps capture the causality, the attack caused the injury. It structures the data in a way that tells a coherent story.
And there's one more tricky element, time. Humans are vague. If I say, the merger happened last Friday, the computer is lost.
Last Friday is meaningless to a database. So the system has to perform normalization. It has to look at the document's publication date, calculate back to find the specific date of last Friday, and convert it into a standard format, like YIMD,
It's translating human time into machine time.
anchoring the event in history.
So let's zoom out. We've built this incredible system. It can read, it can identify Fred Smith, it knows he works for Fugu Motors. Why does all of this matter? What's the application?
The applications are just massive. Let's start with healthcare. Hospitals produce mountains of text,
All those doctor's notes.
and it's all unstructured. Patient complains of chest pain, prescribed aspirin. We need IE to extract the diagnosis, the treatment, and the outcome. You can't have a human read every single file to find out if a treatment is working across a whole population.
So it's literally saving lives, but reading the notes we don't have time to read.
In a way, yes. And the source also mentions genomics. This goes back to a vision from 1959. A linguist named Zelig Harris imagined indexing scientific journals.
And now we have to.
We have to. The field of biomedicine grows too fast for any human to keep up. Thousands of papers on gene and protein interactions are published every week.
So the computer reads the papers for the scientists.
It extracts the interactions. It finds gene A activates protein B and builds a database. It accelerates science by synthesizing the literature that no one person could ever read.
And, of course, there's the news.
Right. Imagine indexing every company mentioned in a day's news, i.e. allows for that quick scanning. It turns the daily news flow into a searchable database of the world's events.
So what does this all mean? We've gone from just spotting a capital letter to understanding complex medical histories.
It really represents a fundamental shift. We are moving from a world where humans read text to get knowledge to a world where humans oversee systems that read for us.
We're building the architecture for machines to understand human history.
And science and daily life.
Yeah.
It's a big deal.
It is incredible, but also a little daunting. And that's where I want to leave you today. We talked about semantic drift, that moment when the machine learns the wrong pattern because of a correlation.
Like politicians in their home states.
Exactly. So if we are relying on these systems to organize human knowledge, to write our history based on millions of documents, what happens when that drift goes unnoticed?
That is the question.
What happens when our index history becomes just slightly wrong and we don't even realize it until it's too late? Something to think about. Thanks for listening to this Deep Dive.
My pleasure.
See you next time.